Welcome back. So we discussed the steps of the BCA algorithm. Now let's see what is the problem. Now we computed the eigenvalues and eigenvectors from the covariance matrix, right? However, calculating the covariance matrix itself by just multiplying the matrix by its transpose, so how we computed the covariance matrix, we just got this matrix and then we multiplied this matrix by its transpose. This can lead to problems, right, in terms of loss of precision and numerical errors. So we might have some information loss in this step, even though we didn't really do any dimensionality reduction. So what I'm trying to say is that if we compute the covariance matrix like this, and then get the eigenvalues, eigenvectors, and use all the vectors to rebuild the data, then you will see that we have some errors, even though we didn't really do any dimensionality reduction. Okay, so we should calculate the covariance matrix using another technique. Instead of multiplying the matrix by itself, we will use a linear algebra technique called singular value decomposition. This is a very famous linear algebra concept. We will not go into the details, but basically what we want to say here, or what you need to know, is that for any generic matrix, right, it can be computed using the multiplication of three matrices: U, S, and V transpose. And U is an n by n orthogonal matrix, while S is a diagonal n by p matrix, and V is p by p orthogonal matrix. And the principal components are the columns of V, and the scores, the principal component scores, or the principal component values, the eigenvalues, are the columns of U. And if you want to know more details about these computations, you can check this blog right here. I will leave it also in the resources, and you will know all the details why we have U, S, and V. Right, it's out of the scope for this course. There is a lot of mathematics behind this. We are not really concerned about all this, but it's important to know that we can compute the covariance matrix using two ways: either by multiplying the matrix by itself, by the transpose of itself, or by doing this technique. And we most probably use this technique because using the covariance matrix or calculating the covariance matrix using the first technique can lead to loss of precision and numerical errors. So here we have x, and as we said, x is n times m, right, from the very beginning. And we said that x is basically u times summation or sigma, and this is basically the c, and then we have v, which is m by m, right? So if you multiply these three matrices together, you will see that we have here, we can multiply this by this because we have n times n, right? So we have here n and n, so the multiplication of this by this will be n times m. Now if we multiply these two by this one, we will have m times m, right? So we have m and m here, no problem, and we have m and n here, so the output will be n times m. Okay, and this is basically, if you want to know more details, we have basically u times u transpose, right, is equal to the identity matrix. V times V transpose is equal also to the identity matrix. This is the identity matrix. We have 0 everywhere and 1 on the diagonal. Okay, so this is basically the singular value decomposition technique, and this is the difference between using the covariance matrix, computing the covariance matrix just like this, and calculating the covariance matrix using singular value decomposition. So if we use the singular value decomposition, then the principal components we calculated using the eigenvalues, eigenvectors, and so on from here are basically the columns of V, the third matrix here, and the principal component scores. What are the principal component scores? The eigenvalues, right, are the columns of U, right? And you can check the details here. So this is the difference between using the singular value decomposition and computing the covariance matrix the straightforward way. Okay, so in the next lesson, we will discuss the main applications of the BCA. So there are some very cool applications that we can use for BCA, and then we will see how we can implement the BCA from scratch for many different applications. So let's go to the next lesson and start seeing the applications of the BCA.